Welcome to this explainer. We're going to unpack the architecture of a full-stack web app, starting from the absolute basics and going all the way up to complete data persistence. I actually love thinking about web development as a layer cake. You can't just slap the frosting on before you've baked the base. So today, we're going to bake that cake from scratch, figuring out exactly what it takes to turn a totally blank screen into a globally accessible, data-driven application.
Okay, let's kick this off with a bit of a harsh truth right out of the gate. A weak foundation will absolutely sink every single later effort, which makes your initial environment setup incredibly critical. The source material hits the nail on the head here. The most expensive bugs aren't usually in your logic. Nope, they're in a setup that nobody bothered to check, and you usually end up catching them in week 3 instead of hour 1. You literally can't build a skyscraper on a swamp, and you definitely can't build a web app if your tools aren't configured correctly.
Here's our roadmap for today. 1. Your essential developer toolkit. 2. Front-end, building the UI. 3. Back-end APIs, the waiter. 4. Databases, persisting the data. And 5. The full-stack web app. Let's get into it.
Section 1. Your essential developer toolkit, building the unshakable foundation.
At the very bottom of our architectural cake, every single project, honestly no matter the language or the stack, flows through these 5 specific tools. First up, you write your code in the editor, like VS Code. Then, you run commands in the terminal to navigate your folders or start your local servers. Third, you're tracking every little change with Git, saving labeled checkpoints of your work. Fourth, you actually execute the code via a runtime, like Node.js or Python. And finally, you manage all your external dependencies with a package manager, like NPM or pip. Get these 5 tools working in perfect harmony, and you are ready to build.
Section 2. Front-end, building the UI. Basically, what the user sees.
So tools in hand, we start building the first floor using structural HTML, visual CSS, and interactive JavaScript. A brilliant example of this is the Personal Expense Tracker Challenge. The scenario here is simple. A small business owner wants to ditch their physical notebook for a web app to manage their spending. But there's a strict rule for this stage. It literally must be built using only HTML, CSS, and JavaScript, entirely in the browser, with absolutely zero back-end server allowed.
Think about how these user interface requirements actually break down in practice. A user inputs an expense, say $50 for coffee, by filling out the name, amount, category, and date. Instantly, that expense pops up in a data table, and the total amount spent updates automatically. HTML gives us that raw structure for the form and the table, CSS makes it look sharp and responsive, and JavaScript? Well, JavaScript provides the magic that calculates that running total on the fly.
Now, to make the app actually robust, we've got to enforce some rules. We use JavaScript for form validation, like preventing users from entering negative money, because that makes no sense, or preventing them from leaving the category empty. We also tap into browser storage. That way, if you accidentally hit refresh, your data doesn't just vanish into the void. But there's a pretty big catch here. That browser storage only saves the data on that one specific device.
Section 3. Back-end APIs. The waiter. Processing requests and applying rules.
So what happens when our app actually needs to share data globally across different devices? Or when a bunch of users need to interact with the exact same information? Enter the API, or Application Programming Interface. Think of it like a waiter in a restaurant. You're the client sitting at the table. You don't just march into the kitchen and cook your own meal, right? You tell the waiter your order, the waiter takes it back to the kitchen, and then they bring out your food. A RESTful API works on this exact same client-server separation. It's stateless, which basically means every single request contains all the information needed, and the server doesn't keep any memory of your past requests.
The really cool part is that APIs use standardized HTTP verbs that map perfectly to the 4 things almost every API does: create, read, update, and delete, what we call CRUD. If you want to read data, you fire off a GET request. Creating new data? That's a POST request. Updating uses put or patch, and to delete, well, you just use delete. It is a beautifully simple, uniform interface.
All right, let's test this out with a real-world scenario. If a user asks our API waiter for an expense record or a task that was actually deleted yesterday, what status code fits that situation? Take a second, think about it.
If you guessed a 400XX client error, specifically a 404 not found, you are spot on. You can officially speak the universal language of HTTP responses. These codes are categorized so logically. 2XX means success, like a 200 OK or 201 created. 4XX means the client messed up somehow, like our 404 or a 400 bad request if a field is missing. And 5XX? That means the server itself completely crashed or had some internal meltdown.
Section 4. Databases, persisting the data, where data is saved long-term.
We're about to hit a massive wall when it comes to our waiter's memory. If our back end only relies on an in-memory array, which is literally just a variable floating in our server code to store all those expense entries, we've got a huge problem. The second that server restarts, crashes, or we push an update, every single piece of data disappears instantly. The in-memory array only lives as long as the active process is running.
And that stark reality brings us to the immediate need for a database. We need a permanent, structured home for our data. Using a relational database like SQLite or PostgreSQL gives us true persistence, so data actually survives a restart. It gives us strict rules for structure and consistency, allows us to efficiently scale up to millions of records, and lets us safely handle access from a ton of users all at exactly the same time.
To keep a database like that organized properly, we rely on a concept called normalization. Think about it like this. Before normalization, you might be repeating a user's name and email on every single expense row they create. If they update their email, you're stuck hunting it down and updating it in hundreds of places. But after normalization, we split that duplicated data into separate tables, a users table and a tasks table. We connect them using a foreign key, which just means the task points back to the user's ID. Now if an email changes, it only ever gets updated in one single place. It's a total game changer for efficiency.
Section 5. The Full Stack Web App. Integration and Deployment.
Finally, we've reached the very top of our layer cake, where every single piece of tech we've talked about unites into one seamless experience. A true full-stack developer connects all of these dots. Here's the complete flow. The user clicks a button on the front-end UI. The API waiter takes that specific HTTP request and runs it to the server. The server talks to the database kitchen, which securely reads or saves the structured data. The database hands it back to the server, and the server fires a crisp HTTP response right back to the browser, updating the screen instantly.
Now that you understand exactly how all these interlocking pieces transform a totally blank screen into a rich, persistent web application, I want to leave you with this final thought. You've got the toolkit, you know how to build the front end, you understand the API waiter, and you can organize the database kitchen. So, what will your full-stack web app serve the world? Thanks for joining me on this explainer, and happy building.